Okay, so now we will go to probably the most difficult part of the job of a data scientist. It's called respecting an experimental protocol or using an experimental protocol. So first I need a concept called hyperparameters. So the model that we will train will have parameters, and these parameters will be fit automatically by our learning algorithm. They are easy parameters to be fit, and they will be fit automatically. There are other parameters, the parameters of the learning algorithm, that are harder to fit. And usually it will be the human that will fit the hyperparameter. It can be the choice of the architecture, it can be the learning rate of the optimizer, it can be different things that it's really hard to optimize automatically. There are some hyperparameter tuning algorithms, and at Mila we are doing some research on a platform called Orion. So Orion implements different hyperparameter tuning algorithms, and we benchmark these different algorithms on this platform. It's freely available, you can check it, but it won't solve the problem of optimizing the hyperparameters because this space to optimize is too big. And what a good data scientist will do is identify some hyperparameters that can easily be optimized by these hyperparameter tuning algorithm, and other hyperparameters that we will use our intuition, our knowledge, our experience to fix it by ourselves. And this is how the students are working to achieve the state-of-the-art results on different benchmarks. They use a mix of the two. And it's part of the machine learning expertise. Okay, so what is the experiment pipeline? So first of all, we are data scientists, and as a scientist, we want to make science. And what does it mean? It means that I will have some hypothesis on probably this model architecture will work well on my data, and I want to prove it. I want to show, to demonstrate that it's the case. So I will define an experiment. Then I will retrieve my data, and I must bring this data efficiently from a permanent storage to the device that will do the experiment. Here it's called the GPU. And we will code the input pipeline. The third step is I want also to visualize the experiments. I want to visualize what are the hyperparameters, what are the performance metrics, what is the evolution of the training of the model. So we will dedicate some time to develop different kinds to visualize these information. The fourth step is to create the training loop. It's a code that is pretty standard that you can reuse in different experiments, and we will provide you an example of a training loop in the tutorials at the end of the day. And if you want to optimize some hyperparameter, you must also develop the hyperparameter tuning loop. So what is an experiment? So the experiment will identify all the degrees of freedom. So they are values that I must provide to be able to reproduce the experiment. So let's say someone comes to me and say, I have 95% accuracy on this task. And I will say, okay, I want to reproduce your result. I want to obtain me to 95% accuracy. What do I need to reproduce the experiment to be sure that there's no errors and that we can be sure that this model have this performance on this data set? So the first thing is to specify the computers. Which computer did you use? Which GPU? The model of the GPU that you are using. The performance can change according to the model. Not a lot, but it's something that is important to know. Second thing is the version of the libraries. You will see in the afternoon that even if you are just using a very high-level environment like PyTorch, PyTorch is really an ecosystem of libraries with different libraries at different levels of detail. And the most basic one is implementing linear algebra on the GPU. And if you use different versions of these libraries, the performance can vary a lot in terms of computing speed, but also in terms of reproducibility. The version of your data set, when you say I have 95% accuracy, it's relative to a specific data set where you evaluated your performance measure. And if you are gathering new data every day and you lose track of the data set that you use, then it can be hard to reproduce the result after that. So you can do a snapshot of your data set in time to be sure to reproduce the experiment. The version of the training code, it's something easy. It's really like when we are doing a software engineering project, we can use GitHub to save the code, and we have a snapshot of the code for that was used for this experiment. Then we enter a little bit more in the machine learning context. What was the architecture that you use? And an architecture can be defined with many modules, and it can be hard to remember exactly which architecture I used and what was the connection between these two modules in an architecture. It can be very hard if you don't record this information. Of course, the values of the hyperparameters that you use. And finally, we use a lot of randomness to train deep neural network. And this randomness is not pure random coming from the computer. Random is simulated by a random generator that would generate a sequence of pseudo-random values. And the random generator are parameterized by what we call a random seed. And if you forget to record the random seed, then an experiment can be not reproducible. So now you must think, okay, there's a lot to record, and if you are already doing machine learning, maybe you're not recording all these values. And in fact, depending on the experiment, not knowing exactly the GPU will not have a strong impact on reproducing an exact value of the performance metric. So there will be like an uncertainty around the 95 that I want to reproduce. If I have 93, it's not that bad. If I have 97, it's not that bad. It just means that I have some noise around this score. And if you want to really have an experimental protocol where you load everything, all this information, I recommend you to use an ML platform, a platform to manage your experiment, like MLflow. And you can see here that on MLflow, I can have one experiment by line. I will have the date and the hour that I launched this experiment. I will have the user who launched this experiment, the source code, a version of maybe the code or the data set, the values of the hyperparameters that I want to try. So here I just have two columns that I want to see if I change one of the two, how my performance metric will change. And here I'm using 3 performance metrics. You don't have to choose only one, but you can choose as many as you want if it's useful for you. Do not use performance metrics only because in the literature they were doing so. Use it if you really need to measure a property with it. Okay, so now you must think that it's a little bit too much to record all this information. But at the beginning, I said that when we specify a task, we are asking what we want to achieve, and we don't define how to achieve it. It's the learning algorithm that will find how to achieve the task. And in fact, for an AI, all means are good to achieve a task. And if there's a way to achieve the task that is easy because there is a bug in your data set or a bug in a simulator, you can be pretty sure that the AI will use this flaw, this bug, to maximize the performance metric. And one of the most famous examples is in reinforcement learning, where it's an algorithm learning to play to an Atari game called Montezuma. So you have this Atari game where we have an agent playing this game, and the agent is pretty good at this point. And what the data scientists discovered after a while is that we asked the agent to maximize the score here, but the algorithm will find a bug in the game that was never found before for, I think, 20 or 30 years of people playing to this game. So we can see that it found a bug, and it will bring the game to a bug state, to a buddy state, where the diamonds are still appearing. So it's super easy to maximize the score because I just have to jump and catch it. I don't have all the difficulty of the initial game. And the learning algorithm found it by itself. It exploits this bug to maximize the score. So this is an impressive examples. But really, it happens a lot in the literature. And people are trying to understand better how the algorithm is solving the task after we train it, after we are sure that it has good performance. And intuitively, if I want to recognize if there's a dot in the image, and the algorithm tell me, yes, there's a dot, and describe why, because of features in this area of the image, I can be confident that the algorithm knows what is a dot in the image. But if the algorithm gives me features that depends on this object, because it's a simpler object and it's highly correlated to the presence of a dot, then I can question really if my model is cheating or not. And it's called verifying the saliency map for interpretation of how the model is solving the task. But it's hard. It really depends on the type of data that you are using, the type of models that you are using. Saliency map is still something that people are doing a lot of research to have a good technique to compute this saliency map. And you should also be critical. It's not because you have a high performance metric value that your job is done. You should be critical to the algorithm and try to find examples where the model will not perform well. And one of the first steps to do so, to try to challenge the model, is to take your data set with examples and to split it in two different data sets. One data set will be called the training set, and the other one is the test set. The training set can be used by the learning algorithm to fix the parameters of the model, to really do trials and error and learn from this training set. And you should never show the test set to the learning algorithm for learning. You just use the test set to evaluate. So you will use examples that the model has never seen during training to test if it's able to generalize. And one way to cheat one way to cheat on a task is to memorize all the examples in the training set. I just memorize everything, and I will have a very high performance metric on my training set. But if I give a new examples, because I just memorize and I don't understand really the task, I will not be able to classify well on the test set. So it's a way to detect if my model generalizes, and it's essential to use this split into a training and a test set for evaluation. And the reason why is, if it's cheating on the training set, you will be confident that the performance are good, and when you will deploy it in production, where new data will come in that are not in the training set, then your model will not generalize. And in fact, you are just overconfident of the performance of the model. Also, I was talking about hyperparameters, that we can do several experiments and choose the best model according to the hyperparameters. It's a good idea, again, to choose the best model in a list of hyperparameters on another set called the validation set. So the training set will be used to learn the parameters of the model, and I will do several experiments on the training set. And then I will use the validation set to take the best experiment, and I will test one last time the best model on another set called the test set. And the ratios here are the ratios of the number of examples I took from my data set, the whole data set, to do this split. So here, 60% for training set, 20/20. It depends on the number of examples of number of data points that you have in your data set.